S3. Okay, so this was something Ig raised for d3x, sorry, d4x1, d4x2, d4x3. Okay, so then we had this propagator I delta f x2 minus x3 I s f x2 minus x1. Okay, then we are having this propagator I s f something x1 minus x3. Okay, so then we had this kind of factor. So this E minus PS, okay, E plus P prime S prime. Okay, so we have then this psi bar of minus x2, and then you are having psi minus I think x1 or x3, and then you are having this 5 plus x1. Okay, and you are having this here. So this is our equation. So we are trying to calculate this. Okay, so now what is the first step we started? Convert your propagators into the Fourier series, is it? And write, okay, we know now this very factor. So this I have already told you yesterday. Huh? So this kind of factor is that exponent, the plane wave simply corresponding to the boson as well as the fermions. Okay, so let's write, let's convert, okay, moving to Fourier space. Okay, so I can write this thing as minus Ig2 d4 of x1 d4 of x2 d4 of x3. Clear? So this I can write as this very factor. Let's go to as a Fourier space. So you are having d4 of q1 divided by 2 pi raised to 4. Okay. So let me club all these momentum integrals together. Okay, so it is d4 of q1 divided by 2 pi raised to 4 e raised to minus I q1 x minus x, x2 minus x3. Clear? So for the time being, I will write these integrals. So this will be actually 12 d4 of q2. This is what we have already written yesterday. Okay, then this will be actually I. Tell me. So it is delta. Okay, so let me write. So it is e raised to. Can you tell me? I q1 dot x2 minus x3. Clear? Then from this very factor, I will have e raised to I q2 dot x2 minus x1. Then I will be having e raised to I. Okay, q3 dot x1 minus x3. Clear? So these are the exponential factors. Now I will write this I delta f q1. Then I will write I sf q2. Then I will write I sf. Clear? So it's all these factors in the momentum space. समझा? So this is okay. d4 q1, this very factor, then delta f q1. It is this. Clear? And the other. I have actually clubbed these momentum integrals together here. समझा? Any problem? Okay. So now what is the value of this very factor? Anybody? Just tell me. So it is. So let me write the value of that very factor. So the initial state is e raised to minus I k dot x1 divided by root of twice v omega k. Clear? So what is the another? Tell me. E raised to I. So x2 is there. So what is the momentum of the electron? P. So it is p dot x2 by root of twice v ep. Clear? And what is the factor? Okay, so another factor is e p prime dot x3 divided by root of twice v ep prime. Okay, then you are having u bar s of p and v s prime p prime. Okay, and then you are having that vacuum. So the expectation value of the vacuum. So this is up to this we have written yesterday. Okay, although we have already evaluated, we had that kind of the minus factor was somewhere. Problem of the minus factor. Now club the terms. Okay, so let me write d4 in. Let me write the x1 integral first. Now, where are the x's? Coordinates are in the exponentials, is it? That means they will yield as a delta function. Let me write those things. Okay. So let me write these integrals so that so d4 of x1. Now tell me where are the x1? It's e raised power minus I q2 dot x1. Clear? So then you are having exponential e raised power I q3 dot x1 and then e raised power minus I q dot x1. Clear? You sure? So these are the exponentials. What is that equal to? Tell me what are these things. So I can write, you take minus out. So nala equal. So it is e raised power minus I q1. Then just tell me. Okay, minus q3 probably because I have taken minus out. Then you are having what? Plus k dot x1. You sure? Is this the case? Huh? Is this the case? Q1, it just comes with the minus sign. Minus I have put outside, is it? Q3, it comes with the plus sign, is it? Q3 is here.
X1 can be common.
Oh, somewhere is an error. Huh? Q1 is not there. Huh? It's Q2. Huh? Sorry. So Q2 and then it is Q3. Clear? Is it right now? Okay, good. So this I can write now 2 pi raised power 4 delta of delta 4. So I can write it as Q2 minus Q3 plus K. But I will write it. Okay, so let's write it as Q2 minus Q3. Let's write it. Similarly, I can have other delta functions. Okay. So let's write the other delta functions. So d4 of x2 e raised power, now tell me, x2 factor e raised power I q1, okay, dot of x2. Where is the next x1? It is minus q2. Then where is the another x2? It's at t, yeah? So it is dot x2. Okay, so let me take minus out. So it will be something 2 pi raised power 4 delta 4. Okay. If I take minus out, what it will be? Q2 minus, or let's write it hardly matters because a delta function is even. It doesn't. Clear? So this is the delta function. What is the next thing? d4 of x3 e raised power. Now let's take x3. It's minus I. Okay. Q1. Where is the next x3? Plus q3. Then what you are having? Plus p dot of x3. Is it true?
Plus Q2 I
Plus? Yeah, plus q2. How? Q1 is Q1, Q2 is. Okay, so it's like going by S check. So delta 4. So it is Q1, Q3 plus P prime. Let me check. Okay. So you are having something. Minus K. Yeah? Is it minus or plus? Just check it. It's minus K. So here is an error somewhere. So if I take minus K, so it should be K minus Q2 minus Q3. Okay. K. So here is this Q2 should be minus. Is it correct? So that's why we are having a problem. Huh? So what are the integrals? d4 x1 contains q2 dot x1. So that comes with the minus sign. Then you are having q3. That's again with the minus sign, is it? Sorry. Q3, yeah? That's with the plus sign. So if I put now, what it will be? Oh, it's okay. Huh? Clear? So let's substitute. So what are the other delta functions? Q1 plus Q2 minus P should be something. It should be minus P. Actually, gadbad karke boलना तो. So minus I. Yes. I have defined in the wrong way. So it is actually minus. So it's minus. Because it is a Fourier transformer. How we define the Fourier transform? So you are having f of x is equal to integral something dk e raised to power minus I kx f of k. Clear? So it's having a minus sign here. Yeah? Okay. So that's why. And so yes. Clear? So we are having a minus sign. Okay. So now what to do? Now change this thing. So x1 will come with a plus sign. Okay. So it's q2 x1. Clear? Then you are having q3 that comes with a minus sign. Clear? समझ? What is k? K comes with a minus. समझ? So it's actually minus k here. So what that is equal to 2 pi raised to 4 delta 4. Let's take k positive. So it's k minus q2 plus q. Because delta is an even. You take minus out, it will be like this. Now let's write this thing, x2 factor. What is x2? It's minus q1. So let's take minus q1. Then you are having this q2. So it's again minus. So that will be plus. So it will be minus because this is a clear. So this is okay. So then you are having q1. Okay, q1 it's minus and plus. So it will be plus. Then you are having q3. That's again plus. Then you are having it's okay. Got it? समझो? Now it's correct. So now each delta function is actually in the product form. So now let's write. So what they yield? What these delta functions yield? They yield actually an overall conservation momentum. Okay. So let me write it here. So what is the delta function? You are having this delta 4 k minus q2 plus q3. Okay. Multiplied by this delta function. Delta 4 q1 plus q2 minus p. Then you are having this delta 4. Another delta 4 q1 plus q3. Okay. Plus e prime. Got it? So this is the okay. So when you substitute it here, it will be in the product form. Clear? So that's what I will just evaluate first delta functions. Clear? To get the overall conservation rule. Okay. Now what you can do? So okay. So let's use the value of q2 from here, or you can use the value of okay. Okay. So use the value of q2 from here, value of q3 from that very delta function in the first one. So it is delta of x multiplied by f of x. You treat this as, let's say, f of x, another as the delta x. Clear? So okay, so if you are not able to settle, understand. Okay, so what this delta function yields me? K is equal to q2 minus q3, is it? And what this delta function yields me? P is equal to q1 plus q2, and the same thing the other way around. What you will use? You will use the values of, let's say, q1 from here and q3 from there. Substitute it here. समझ आओ? Treat one as a delta function and another as the function. समझ आओ? This is the how we evaluate the delta function. So I can write this as delta 4 k minus. What is the value of q2 from here? So
P minus Q1.
Okay, P minus Q1. Okay, so it will be like this. P minus Q1. What is the value of Q3 from the other delta function? Okay, so it is minus Q1 minus Q3. So keep other delta functions as such. Q1 plus Q2 minus P delta 4 Q1 plus Q3 plus P.
P prime.
Okay?
P prime.
Yes, it is P prime. Where?
Second one.
Yes.
Q3.
Q1 minus, okay, Q1 minus P. Okay, good. Great. Hoshar hai. Okay, so now this Q1 and Q1 cancels. समझ आओ? So what we get? Okay, so let me write it here. So let's do. Okay, now this delta function gives delta for k minus p prime. Is it? So what that gives me? A conservation of the momentum, total conservation, is it? K is equal to p plus p prime, is it? So let me write it here. So let's evaluate. So therefore this S3 Fi I can write as minus IgQ. Okay, so these are gone. Now you are having 2 pi raised for 4 everywhere, so it will cancel with this thing. Okay, so this is now gone. So what remains there? So the integrations over this d4q1, d4q2, d4q3. Okay, so then you are having the delta functions. So delta 4 k minus p prime. Okay, so from this very delta function, then you are having this delta 4 q1 plus q2 minus p, then you are having this delta 4 q1 plus q3 plus p prime. Okay, so it's all these delta functions. Now use this I delta f q1 ISF q2, then you are having ISF q3. Clear? So then what you are having, all these factors are gone, these exponential factors. So you are having in the denominator. Okay, so multiplied by this factor, 1 divided by root of twice v omega k, 1 divided by root of twice v e p. So it is a straightforward calculation, you need to do it at your places. Okay, then you are having this thing, USP, URSP, VS prime. Okay, Samasha? Okay, now look here. So this delta function there is no integration over the variables of this delta function. Clear? You can take it out. Samasha? What I will do, I will put a 2 pi raised power 4 in fact front of this delta function and divide it. Samasha? Okay, so let me write it this way. Okay. So this I can write as minus Ig whole cube, okay, 2 pi raised power 4, okay, delta 4 k minus p prime, okay. So what remains there? Now what I will do, just integrate over, let's say integrate over q3, okay. So you take one delta function out, it is the overall conservation of the process, integrate over q3. So you are having q3 here, is it? So what q3 gives me? q1, okay, minus q1 minus p prime. So that means this will be replaced by minus q1. Okay. Okay. So then, okay. So let's take integration. So d4 of q1, d4 of q2. Okay. So let me write the I. So you are having then delta 4 q1 plus q2 minus p. Okay. So you are integrating over q3. So it will be I delta f q1 ISF q2, clear? So that will be ISF, okay, what it will be? Minus q1 minus eta, and then you are having all these factors. So 1 divided, okay, so let me have all these factors, so let me call this as factor, huh? So Shama, so because I have to write it, it wastes time. So now let's integrate again over this delta function. I will show it in a diagram again. No issues. Let's integrate over this delta function. Let's integrate over q2. Okay. What will happen to q2? Q2 will be replaced by q. Okay, p minus q1. Okay. So that means this will be replaced by p minus q. So it's equal to minus Ig whole cube 2 pi raised power 4, okay, delta 4 k minus p prime. Now look here, all these factors what you are having there, okay, these I mean the factor what I have written, there is no integration over that factor, clear? So Okay, so I will write that here. So I'll be having 1 divided by root of twice V omega k, 1 divided by root of twice V EP, 1 divided by root of twice V EP prime. Okay? Clear? So now let's write this thing. So it will, okay, because I have put this 2 pi raised power 4 outside, you need to divide this by 2 pi raised power 4. Okay? So it is d4 q1 divided by 2 pi raised power 4. So it is I delta f q1. Okay, since you are integrating over q2, q2 is replaced by p minus ISF. So it is p minus q1. Okay, then you are having ISF minus q1 minus p prime. Okay, multiplied by, okay, so let me keep it as such. This thing multiplied by this u bar s p v s prime. Clear? So this is our the Feynman amplitude. Sorry, not Feynman amplitude. The scattering matrix element for our loop diagram. Clear? Now look here. So these are actually the kinematical factors. Is it? So they are simply the variables. So they do not represent what is the kind of process. They simply represent overall conservation of the momentum, and you are having these factors, the energy factors multiplying. They are kinematical variables. Now what are the variables that describe our process? So that u bar and v, is it? U bar is a function that describes the outgoing electron. V is a function that describes what? Outgoing positron. And you are having in between the internal lines of the diagram that are shown by this thing. So it represents your dynamics, because these are the propagators. Propagator simply signifies the dynamics of the system. Samushaman? And the kind of interaction is given by this G. Is it coupling constant? What kind of interaction you are having? So except this thing, whatever the factors you are having, they represented the Feynman amplitude of the process. Samajhava? Okay. Now look here. If you look at these three delta functions, they actually represented the conservation at each vertex. If you see. So forget about, okay, so we had actually three delta functions without this k minus p prime. What were those delta functions? So everybody has written it? Okay, so what were those delta functions? The initial delta functions. Okay. So this is p prime. Okay. So then this is p. So let's put the direction here. So what you are having? So what was the delta function at x1 when we integrate over x1? So let's call this as x1, and then you are in probably this x2 and this is x3, yeah? Something. So is this x1 point? So this is x2. This is. Okay. Now what was the delta function here? Delta 4.
Q2 minus Q3.
Q2
minus Q3.
minus
Q3
Q3
minus Q.
minus K. Clear? Or K. Okay. So let me write it as, it is like K minus Q2 plus Q3. Is it? So it is the conservation here. You are having Q coming from here. So what you are having? So tell me the delta function here.
Delta 4.
Okay. So you are having here delta 4 Q1 plus Q2 minus P. Is it? So P is going out. What it means? So you have to adjust these Q1 and Q2 such that at this point, what you will get? P is equal to Q1 plus Q2. So much here. So let's say for one propagator, let's say if this is Q1, this is Q2, and this has to be something Q3. Clear? So what is the delta function here?
Q1 plus
Huh?
Q3 plus
Delta 4
Q1 plus Q3
huh? Q1 plus Q3 plus P prime. So that means P prime is equal to what? So what is the direction of then this?
opposite.
Huh? Obviously it is, because this P prime is actually my, okay, so this is P prime. It is actually the outgoing P prime. Huh? So this is outgoing P prime. Huh? Okay. So it means Q1 plus Q3. So if I put the direction here, so what you should get? P prime minus P prime. The minus P prime is actually moving outwards. Since for the positron you are having P prime this way, that means if you put now the momentum, that's actually minus P prime. Sure? Okay, so look at here. What you are having? You add Q1 plus Q2. What you should get?
P.
Okay. So this is the direction. So what about this thing? So if you are coming now this way, so what you should get?
Q2.
This Q2 should be actually sum of K1 plus, sorry, this K plus Q3. Is it? Q2 is equal to sum of K plus K3. I mean this Q3. So not that so much. Now all these arbitrary, you can put the arbitrary momentum in a diagram, and at each vertex you have to satisfy the conservation rule. And this leads actually the overall conservation in the process. Samajh? So that means in a given diagram, conservation rule will be satisfied at each vertex. Okay, now let's look at, now this is our total, the amplitude. What we have removed? Q2 and Q3 are removed from this very, this SF. This matrix element. Clear? What remains there? There remains only Q1. So that means you are having only Q1 here. And you have adjusted because of the conservation in the process, okay, you have to adjust, okay, the momentum of the internal lines now. We will see in a moment when we will discuss the Feynman rules. Okay, so you are having here one loop. If you look at the tree diagram, that was without loop. Clear? So you don't need to consider any kind of arbitrary momentum. What is, you are having an integration or momentum here. So much just understand this thing. This will help you to understand a Feynman rule. Okay. Now you are having one loop here. Okay. One loop says you put one momentum on an internal line. Clear? And then adjust the by conservation rule at each vertex. Adjust the momentum of the other lines. So what you are having? Q1 at one line. Now what you are having P prime here. Okay, so by that very process, look at that. What is the momentum here? What is the momentum here? P minus Q1. Clear? Now if they add here, what you will get? P. What is the momentum here now? Minus Q1 minus P prime. So now these two will give you this thing. So they will give you actually the overall conservation. Isha? You got my point. So what you have done? You have actually adjusted. Okay, now P and P prime. Okay, you can write this Q minus P prime in terms of K. It doesn't. Okay, so it doesn't matter. You can put here in terms of the K. It hardly matters. Huh? Can you put it? You can put it in terms of K in such a way that the sum of these two yields you this thing. Samajh? Can you do it? What I am saying, okay, you can put the momentum on this line in terms of K. How? Such that the sum of these two factors will yield you this thing. So now tell me how I can put it. Now tell me in terms of K. So what you will get? K. What is that? Huh? The sum of these two should, okay. Yes. So you are having plus P here, is it? So then what you will write? K minus P plus Q1, is it? So you can put it like this thing. P minus, okay, you can put this way. P minus K. Okay, P minus K, is it? What is the sum of the two? That's P. What I need to adjust it? So this is a way to fix the momentum. Okay, you can put, let's say, instead of putting Q1 here, you put it here. Then adjust the momentum of the internal lines in terms of the external lines. So this is how we specify the momentum on the internal lines of a given diagram. Got it? Okay, so what the examples I have given you, so they give you that kind of idea when you evaluate the momentum. These momentum integrations. Okay, now look here. In a given process or in a given matrix element, what you are having? You are having an overall conservation of the momentum. you will be having actually number of delta function arising at each vertex, and each vertex will provide you a delta function that will represent the conservation law at that vertex. Okay, but you have to get a one delta function that represents the overall conservation of a process. Samajh? And remaining you integrate out. That's what I have done. I had here 3 delta functions and 3 momentum integrations. Clear? So much because of 3 vertices. 3 vertices gives me what? 3 delta functions means 3 conservation rules. And I have taken 1 for the overall conservation and integrate over the remaining 2. And how many momentum integrations remain then? 1. So much? Okay, so let's figure out the Feynman rules. Okay? Before doing that, let's write the Feynman amplitude first. Okay, general form. If you have any question here, just tell me. Okay, so let's write this thing. Feynman amplitude. Okay. So I can write now my S, the scattering matrix element. If you remember, this S matrix is actually 1 plus I times d4 of minus I d4 of x hi of x plus other term. So when I put the matrix elements, so I'll be having a matrix element corresponding to this identity. Clear? What are those? Those are Kronecker delta functions. I means nothing. So this identity means nothing. A particle comes and goes. It does not have any kind of interaction. So let me write this scattering matrix element. It means like this in final state Si. So I can put it this way. So corresponding to this identity, I will put delta S, delta F1. Clear? And for the rest of things, what I will do? Okay, you have seen in the two calculations. So there is an overall conservation of the momentum. Clear? So when you evaluate these terms, so you will get actually the overall conservation of pole momentum in a given process. Okay, so let me write that. So it will be like this: 2 pi raised to 4 delta 4. Okay, let's say you are having n particles in the initial state. So that means the total momentum of the initial state minus total momentum of the final state. Is this the conservation rule? And then you are having these kind of factors for each initial particle. Twice V, let's write EI as the initial energy for the initial particle. So we have this kind of factor. So for if you are having, let's say, number of initial particles, so for each initial particles you will get like this thing. And then you are having the same factor. So this means the product. Okay. So for final particles, that's right. Yeah. Is it? So in the process we considered, you are having initial 1 particle and 2 final particles. That means you will be having 1 divided by twice V EI, only 1, and 2 factors here. Okay. So then what you are having? You are having a coupling constant that represents a process. So let's put that. So all those factors which, okay, so these are the kinematical factors. All those factors which gives actually the dynamical perspective of a given process, that we write it in terms of this thing. So let me keep this in terms of these braces and put all the rest of the factors as IMFI. So it will contain the coupling constant at a given order of perturbation. It will give me that the factors for the external lines. It will give me the propagators as well. We call this very factor as the Feynman amplitude. So let's look at what we have done at our process. Clear? So that means a scattering matrix element, I can always put it in terms of what? The Feynman amplitude. It means if I know the Feynman amplitude of a process, I know actually the scattering matrix element. So you will see actually we will be only dealing with now the Feynman amplitudes. For a given process, we will be setting up we will be setting set of rules some kind of rules, what we call the Feynman rules. From Feynman rules, we understand how to write the Feynman amplitude of a given process. You don't need to do all this kind of calculations. Okay, just looking at the diagram, you should be able to figure out what is the Feynman amplitude. Okay, so let's do it. Yeah? Let's first write what we have already done. Yeah? What is the Feynman amplitude of the given process? Okay, so let's take this thing. I mean the lowest order. I mean for our lowest order B to E minus E. Okay. So what is the diagram? So this was the diagram. Okay, you are having here B of K, then you are having E minus PS, then you are having E plus PS. Clear? Solution. And the coupling is G, we write. So now tell me what is the Feynman amplitude here. So that we have calculated. So just look at the calculation. So that is simply IG. Clear? Then you are having that US bar P. For the external line, VSL. Yes, so look at the calculation what we had done. Okay, so there in that very calculation, our SFY was 2 pi raised power 4 delta 4 P minus, let's say K minus P prime, is it? And then we are having this factor, then you have this kind of factor, is it? So this we call it Feynman amplitude. Now look here, in the Feynman amplitude when we write, so for scalar boson, whether it is an initial scalar boson or the final scalar boson, there is no factor, clear? Only there is a factor corresponding to the fermion and the anti-fermion. So, samajh aa? Okay, now let's look at the other thing, other diagram. So, just what we have calculated. Okay, so the third order term is what? So you are having this diagram. Clear? So you are having this P of K. Okay. So this is E minus PS. Then you are having this E plus PS. Clear? So now how you write the Feynman amplitude? Now tell me. You have just calculated. So there will be a coupling constant is something IG raised power 3. Clear? So now what was there? There was an integration factor. The integration over the momentas, internal momentum, is it? Or the propagators what are in the diagram. So what was that? So it is G4 of Q divided by 2 pi raised power 4. Okay, so let me write it. Then you are having this I delta F of Q. Clear? Then you are having okay, I SF, okay, P minus Q, I SF P minus Q minus Q. So I have just rewritten, I mean instead of Q1, so you put here as Q. So what you are having the other? So this is P minus Q. What this will be? P minus Q minus P. Clear? So if you put the direction this way, so Isha, is it? So I just relabeled the momentas, and then you are having the factor U bar SP and B S prime. Clear? So samajh aa? This is the factor just we have calculated. Okay? Okay. So now let's write the Feynman rules of this very process. Okay, why we require the Feynman rules? The point is that if I know only the interaction from the interaction, okay, doing all this kind of business, it is a very hectic job, is it? It is a very huge calculation. What you do, if you know the interaction, what is the form of the interaction? Based on certain rules, you derive actually all the Feynman amplitude. Instead of doing all this calculation, so you just look at what is the nature of the interaction or how, okay, what is the form of interaction I should say. Okay, from that interaction, using the Feynman rules, you should be able to write the Feynman amplitude. Okay? The amplitude for the given process. If I know them, I can calculate everything what I want. Okay, so let's write. Okay. Then we will use these rules to look at, the final amplitude. Okay. So I will use left hand side of the diagram. Let's say if you are hanging, okay, okay. Let me use the left hand side of the diagram as the initial particles and the right hand side of the diagram as the final particles, and the time flows in this direction. In particle physics, you are taking time in the upward direction. Okay, समझ आओ? But we will use time in this direction from left to right. Okay, so let's write what are the rules. So first rule is how to write the internal lines. Okay. Since we are, okay, so remember this thing, we are doing a perturbative calculation, clear? So in this perturbative calculation, the number of vertices, okay, so let me write the first rule here. Let's write the first rule. Number of vertices of a diagram is equal to the order of perturbation. So let's say if you are having one vertex, that means you are at the first order. Okay, if you are having two vertices, you are at the second order of perturbation. We have seen actually one vertex and three vertices. The third vertex diagram was actually at the third order of perturbation. Clear? Okay, so now let's represent the internal lines. Okay, internal lines gives you the propagators. Clear? So let's say you put a diagram. Let's think. So this is the part of the diagram. This is a vertex. Okay, internal lines actually connects the two vertices. Samushaman? You got my point? So let's say this is a vertex. That means you are having an initial particle coming from here. Then you are having another vertex out of which the other final particles release. Is it? So that means this represents the inside of the diagram. So okay, so these are the two vertices. So between the vertices, I represented by dotted line. I represented the scalar this I delta f. Okay, so if it is x1 and this is x2, so it will be x1 minus x2. Okay, you can put it in the momentum space as well. Huh? So because we are doing actually in the, okay, so if there is a momentum p, so you write it. So this is same as I delta f. Clear? So this is the scalar propagator. Scalar propagator is shown by a dotted line and internal dotted line. Now let's write the propagator for the fermions. Then for photons, that I will take the later on. So this is by the dotted line. So it is shown by the arrow. Okay. So it means what? There is a flow of momentum in this very direction. There is no arrow defined on the scalar propagator. Samajh, it is your choice whether you put it this way or that way. So there is no need to put an arrow. It will depend on the diagram which you are considering. Okay. So but for this thing, there is an arrow coming from the left hand side to the right side. Okay. So if there is a momentum p, so this is your electron propagator, right? Or the fermion propagator. So it is IS. So now let's try the initial and the final particles. It's really not actually the direction of the propagator. It means where is psi. If you are having psi and psi bar here, because the propagator is the vacuum expectation of psi and psi bar. Clear? So you are having psi here and psi bar here. That means you are annihilating an electron here and creating it back at this very point. So and in the reverse way, you are actually creating an antiparticle here and annihilating that antiparticle here. So that's why you require the direction of the momentum. Okay. So the fermion propagator, you know, since the fermion field consists of two types of particles, a particle and an antiparticle. When you write the fermion propagator, propagator itself means actually you are creating a particle somewhere. Sorry, you are annihilating a particle somewhere. It propagates in space and time and is getting created at another point. Clear? So when you take the fermion, so because in this very field you are having two types of particles. Let's say if you are annihilating an electron, okay, the propagator can be viewed as this way. You annihilate an electron at a given point and create it at the other point. Okay, but it contains the positron field as well. So positron as well. So it is actually the reverse of that thing. So you are actually, while you are annihilating the electron, you are actually creating what? Positron. And while you are creating the electron, you are annihilating the positron. The Feynman propagator for the fermion field gives you that kind of description. Okay? So it means both the things. समझ आया? But in case of the scalar propagator, it's not that. It contains only one particle. So you are having what? A particle being created here and annihilated here and created here. समझ आया? So let's write the external lines. Okay. So let's take this as a vertex. If I put a line on this side, it means the left hand side. Okay. If I put the line on this side, it means right hand side. That means I am saying left hand side lines are what? Initial particles, and the right hand side lines are what? Final particles. Now if I write a line this way, now tell me what it means. So I am putting an arrow this way. So it means a particle is leaving the diagram. समझ आया? When the particle is leaving the diagram, it means it is a final particle. समझ आया? Okay, so I will write for the electrons. Okay, for the fermions, I will show them by the solid lines. समझ आया? Whether you are having the initial particle or the final particle, fermions, both fermions as well as the antifermions, they are shown by the solid lines. समझ आया? So for this kind of thing, this is an outgoing object, is it? So it means I will write it in terms of U bar S. Is it U bar? So U bar S. So this is our, okay, so this represents our final electron. Okay, final state. Now if I am having this way, so this is an electron coming towards the vertex. So what it means? This is now the initial state. So this is an initial particle. So this I write as US. So the factor corresponding to these lines are what? U bar and U. So this is our initials. Okay, now let's look at, okay, so these are the fermions. Okay, so let's take the antifermions. Okay. So if I am having, let's say, so this, okay, can you tell me what this line represents? It's not leaving. For the fermions, sorry, for the antifermions, the direction of arrow is opposite to that of fermions, clear? So you are having a fermion arrow this way, clear? And you are having a line that's on the right hand side of what? The vertex. And the arrow is going through. It means an antifermion is leaving the vertex. समझ आया? So you are having, so this is an antifermion, this is the final state. For final state we put as Vs. So let's write E plus Vs. So this is our final state. Okay, so now what about this thing? Okay, so this is our initial state. S. So this is our V bar S. So everybody got it? Okay. So now you know in diagram what you are having. Okay. So if you are having, okay, so these are for fermion. For bosons, so if you are having boson like this thing, if you are having boson like this thing, so this is the final state boson. This is what? Initial. For bosons, for scalar bosons, we have no factor. We have no factor. Correct? So there is no quantity that represents what? These bosons. Okay? There is nothing like these U's and V's. समझ आया? Clear? Okay. So now let's count the numerical factors. Because if you look, we are having the numerical factors in each of the diagram. Clear? समझ आओ? We will count actually which numerical factors which are associated with actually those delta functions. समझ आओ? So and we will count how many momentum integrations are in a given diagram. Clear? Okay. So let's try to calculate this. So if you have any question, just tell me. Okay. So now let's count the number of these 2 pi raised power 4. So let's count the. So let me write. We are having another as numerical factor. Let's count these factors. So you are having 2 pi raised power 4 popping in, is it? So we have seen in the processor this 2 pi raised power, how many are they? Okay? समझ आओ? How many are they? Okay, so let's count. Let's say, okay, so let's say you are having n is the number of vertices. Vertices in a given diagram. Okay, so that means at each vertex what you are getting? A delta function. No, let me write instead of, let me write V is the vertex. V is the number of vertices. So n I will specify with for the propagators. Okay. So let's say you are having how many vertices? V is the number of vertices. Okay. So since there is a conservation rule at each vertex, so you are getting that 2 pi raised power 4 and delta function. Clear? So what? So it means how many 2 pi raised power 4 you are getting? So you are getting 2 pi raised power 4 to up to V times. Okay. So these are V times. So it means 2 pi raised power 4 V. Okay. So these are the number of vertices. Now there is these are number of 2 pi raised power 4 factors. There is another way we get actually these 2 pi raised power 4. When we convert the propagators into momentum space, is it? dq by 2 pi raised power 4 is also there, is it? So we are having 1 by 2 pi raised power 4 factors as well. So let's say if we are let's say n is the number of propagators. Okay, so it means in momentum space we are getting what? 1 by 2 pi raised power 4 factor with each propagator. Clear? So how many more 2 pi raised power 4 here? So it means I am having total of 1 by 2 pi raised power 4. How many? Raised power n. So that's actually 2 pi raised power minus 4n factors from here. Okay? So समझ? Now for an overall conservation rule, okay, so let's write how many total now? Let's take total. So it is 2 pi raised power 4v into 2 pi raised power minus 4n. Okay? So there is another factor which is contributing. So when I write the total conservation of the momentum in a diagram, I put 2 pi raised power 4 outside the Feynman amplitude. Is it? Is it true? So I keep 2 pi raised power 4 with the delta function. You have seen in those two calculations, is it? So we keep 2 pi raised power factor outside the Feynman amplitude. Okay? So therefore total number are how many? Total number of 2 pi raised power 4 factors. How many are they? So it is 2 pi raised power 4 nu minus 4n, then you subtract 1, so minus 1. Sorry, it will be simply 4 because you are subtracting one of the factors, is it? So it's like this. You have to subtract 2 pi raised power 4. So subtracting means what? So you divide it, so if you are not able. So how much is that? 2 pi raised power 4 into nu minus n minus 1. Samusha? Is it? So you take 1 2 pi raised power out and divide here. Yeah? Okay. So now we can show, okay, it's a well-known theorem in this thing, Euler theorem probably. So let's say if you are having L is equal to number of loops in a diagram, then we can show this thing nu minus n minus 1 is equal to minus. Okay? Let's check it. Let's check it whether it is correct or not. Okay. So let's take your having number of vertices is 1. Okay? So if you are having one vertex, how many loops are there? Sorry, if you are having one vertex, so how many propagators are there? 0. So okay, you are having, let's say, number of vertex is 1. Clear? So take the tree level diagram what we are having. So how many vertices that are having? 1. So now tell me what is the number of propagators? 0. There aren't any propagators. Now tell me what you are having from this thing. So minus L is equal to 1, minus 0, minus 1. How many are they? L is equal to 0. So that means you don't have a loop. So you know in a tree level diagram there is no loop. Now let's take the another case. Let's say you are having 3 vertices. How many propagators are there? 3. Okay. So how many loops are there? So you are having 3 vertices minus 3 propagators. So that will cancel. Minus 1 is equal to minus L. L is equal to 1. How many loops are there? 1 loop. So that means you will be having like this thing. Okay. 2 pi raised power. Okay. Minus 4. These are the number of factors that will come 2 pi raised power 4 in the Feynman amplitude. We are not considering the scattering. This S matrix element. We are considering it where? In the Feynman amplitude. Samajh? Okay. So now let's calculate the momentum integrations. How many are there? I need to figure out because we have seen in that one loop diagram there is one momentum integration. Now let's say if you are having L number of loops, how many momentum integration will be there? Okay, let's count them. Okay, can anyone tell me how many? So we are almost done. You don't need to. Now let's cover the momentum integrations. Tell me. So let's take the momentum integration. Where from the momentum integrations come? When we converted the propagators into what? Coordinate space propagators we are converted into the Fourier transforms. Is it? Let's say if you are having n number of propagators. Okay? N is because we have denoted n as the number of propagators. Samasha? Clear? So what it means? It implies you are n momentum integrations. Because you have converted propagators into where? Momentum space. It automatically means you are having n number of momentum integrations. Okay? But since there are how many delta functions? No, how many are there?
V.
So there are, yes, there are V number of delta because each vertex contributes to delta function, is it? So you are having a conservation law for each vertex. So for each vertex, you are having a delta function. So it means you are having how many delta functions? V delta functions. Clear? So but we out of this V, we keep one for outside, is it? So how many delta functions are remaining? Okay. So you keep one for overall conservation. Okay. So it means you are having total delta functions is equal to nu minus 1. Samashama? Now you need, how many momentum integrations are there? N momentum integrations, and you have to integrate over now delta functions. How many are those? Nu minus 1. Everybody is getting it? So now let's integrate over nu minus 1 delta function. Okay? So integrate over how many? Integrate over nu minus 1 delta functions. Gives us how many momentum integrations? Gives us remaining momentum integrations. Because once you integrate our nu minus 1, you are having n momentum integrations. So you will be having remaining how many? N minus. So remaining are how many? N minus nu minus 1. So that is n minus nu plus 1. So how many are there? Is it? So how many momentum integrations are there? Number of loops. L is equal to number of. So that means the number of loops, the number of momentum integrations. We have considered only one loop. How many momentum integrations? One momentum integration. Is it? So now tell me what is the overall factor? So you are having 2 pi raised power minus 4L. Is it? So and you are having the same thing. So that means each this momentum integration carries 2 pi raised power 4 factor. Is it? So in other words, we will be having this kind of factor in our Feynman amplitude. Okay, so we will be having d4q divided by 2 pi raised power 4. Okay, L times. Our samajh? Okay, now what about the vertices? How to write the vertex? Okay, so vertex gives you the type of interaction. Okay, you put a factor for a vertex. You put, let's say if G is the coupling constant. Okay, let's say the G is the coupling, that specifies the strength of the interaction. Vertex actually gives you the strength of the interaction. Okay, and let's write G as the strength of the interaction. For a vertex, put a factor of minus IG. So you put a minus I factor there. Okay, so these are all the set of rules which specify a given diagram. Now let's try it without going to the detailed calculation. Let me give you a diagram. Let's figure out what is the rule. Okay? Okay. So let's take this tree diagram. The same tree diagram. That way you can understand it. Okay? So let's take this diagram example. So you are having this diagram, the same diagram. So so now you need to specify which is a fermion and which is a boson. Clear? So let's say, so this is an incoming particle. Okay, let's specify, let's call the momentum for this particle as k. Clear? So now these are the two external lines. If I specify like this thing, what it means then? Okay, if I specify these arrows, it means this is an outgoing electron, this is an outgoing positron. Clear? So if let's say G is the coupling, if G is the strength of the interaction, then what I have to put for the vertex? Minus IG. Samajh aaga? Now let's write the Feynman amplitude. So Feynman amplitude, we write I times mf. So now let's write it. How to write the Feynman amplitude? I have to put the factors corresponding to the lines of a diagram. Now for the scalar boson, there is no line, is it? So there is no factor. Then what you are having? Vertex. So let's write the vertex as minus Ig. Then what you are having? External fermion. For the external fermion, you are having the factor U bar as P. So let's say if this is a P, this is let's say P prime. Clear? You can put your labels. Then for external this thing, it's GS prime. Okay, because they are fermions, that's why I have specified the spin. Is it correct? Okay? This is the Feynman amplitude. Now let's go to this loop diagram. I will give a different loop. The other loop you will calculate. So let me take this kind of loop. So this is also the same process. It's having this diagram as well. So this is a little bit. So let me specify the arrows. Clear? I have specified the arrows. So what? Tell me. Okay. So these are the vertices. Okay. Let's say the coupling is G. G is the strength of the interaction. Now tell me which is the outgoing. Okay, which is the incoming boson? Dotted line. So let me call the momentum on this boson as K. So which is the outgoing fermion? So this is the outgoing fermion. Let's call this as E. Okay, E minus PS. Clear? Because it's a fermion, it carries spin as well. So what about this thing? Outgoing positron. So it is A positron, P prime, S prime. समझ आओ? So what about these? These are the internal lines because they are connected between the vertices. So these are two fermion propagators. I have put it as an arc. If you put it this way, so that makes no sense. That's why I have put it this way. So these are two fermion. Let's put the arrow here. It's your choice now, because at each vertex you need to preserve the conservation. So समझ? Here how many loops are? One loop. Oh, two couples. How we loop? We are having one loop means complete circle. Huh? So you are having one loop here. That means how many momentum integration will come out? One moment. That means one unknown momentum you have to put. Okay, to satisfy the conservation. Let's say if I put Q here, so what should I put here? So it should close now, is it? So it should be Q minus K, is it? So at this very point, you have to sum up, it will give Q. So what should be the momentum on this very part? It is K again. So you sum up the two, what you will get? You have now put an unknown momentum here. On unknown momentum, what you have to do? Tell me what you have to do. Integration. That's what I have said, the numerical factors. Okay? So let's write the final amplitude for this very process. IMF. So first what you will put? What are the vertices? For each vertex, what you will put? Minus times Ig. So it is how many vertices are there? 3 vertices. Then you put actually the momentum integration. Let's put the momentum integration first. Is it? Okay. So on which I have to put the momentum integration? Q, the unknown momentum. समझ आओ? So let's put the momentum integration on the unknown case. So it's d4 by q. You are having only one loop. That means only this kind of factor. So now you have to specify the propagators. Is it? So this is a fermion propagator. Is it? So what I have to write? ISF. So q. What is the momentum on that? Then the next fermion propagator ISF q minus k. Then what is the next propagator? I delta f k. Right here? Now what you have to put? You have to put the factors for the external lines. So for the external line, this does not have any kind of factor, is it? So for this thing, you have to put a factor. So what are those? Multiplied by U bar SP, then B S prime. Okay, so this is the final amplitude for the process. Now if you know the diagram, from the diagram you can calculate what? Final amplitude. So समझ आओ? So do it for that kind of diagram. Huh? So this will be the assignment. Huh? Okay, so you are having K here, P S here, and P prime S prime here. Okay, so do the Feynman amplitude for this kind of process. Okay, so समझ आओ? Okay, so we will be taking now the decay. I mean